Hello, and welcome to my talk, Docker for Fun and Profit. My name is Quinn. You might know me from the Java Posse, but a lot of the work that I've done related to Docker has been at my real job at Riot Games. Pardon me. So all of the source code and text and some of the notes for this talk are on my GitHub account, see Quinn, so you can find it at DevOps 14 project there. If you want to follow along or just look for it later. And when I get the actual slides, all finished afterwards, I'll put them up somewhere, probably there as well as up on SlideShare. So the schedule today, I'll talk a bit about, just give everybody an overview about Docker so that we can kind of have a general common understanding of what Docker is. And that's sort of just a traditional slideshow. Then I'll go in and we'll talk a bit more about using Docker, so how to get it set up on your computer, how to start playing with it. So I'll go through with lots of little code samples and things you can play with Docker. And at some point we'll have a break, and then we'll move into playing with Docker sort of at a bigger scale, sort of a clustering scale. I'll show a few examples of how to do that and walk through some architectures of existing systems that are building or attempting to build big clustering systems around Docker. So first we'll talk about Docker. What is Docker? How many people are already familiar with Docker or are using it already? Just a few? Okay. So a lot of people really probably just heard about it and don't really know what it is. So it's the simplest way to describe it is just a way to package applications and to deliver them and run them in a Linux environment. It's sort of a combination of Linux containers and file system containment in a complete package. But let's back up a little bit and talk about kind of why we want that and what is the problem we're trying to solve with Docker. So the challenge is we have lots of different kinds of software we like to deploy, or we need to deploy, different kinds of system libraries that go with our software, different kinds of languages we're writing in, different kinds of configuration and ways of configuring it. And the software has just different ways of running. Is it it's a long-running service? Is it a batch job? Is it a front end? Is it a back end database? Does it have storage? Do we have to worry about? And at the same time, we have just an equally large number of different kinds of hardware environments. Development machines, dev machines, maybe they're virtual machines, maybe they're dedicated hardware. Racked out in our data centers, or maybe they're a customer's data center or a partner that we don't control, and we've got to work with their constraints about how to manage binaries or how to talk to hardware switches, networking. Or maybe we're doing cloud, public cloud, private cloud, hybrid. So we have all of these different combinations of complexity. And the problem with the situation as it is now is we end up with this matrix. So for every single app, how you want to deploy it onto different kinds of hardware and different kinds of environment, you end up with this multiplication effect that's really undesirable. So whenever you add something new, I want to add a new kind of app to my system, I have to use different kinds of tools. I realize I've got to repeat those tools on every piece of hardware, every different kind of hardware I'm going to deliver. Or on the other hand, if I want to add a new kind of hybrid cloud system, I've got to think about every single app. How is that going to be? How am I going to deploy all of my different apps onto that kind of hardware infrastructure? So let's kind of go back and look at another industry that had a similar problem. The transportation industry started out, for hundreds of years, we've been shipping things, carrying things on, wagons and trucks and trains and ships. And everything was packaged kind of in their own way. So things in cans or in barrels or bundles or baskets. And whatever that delivery was, whatever that product was, it had its own kind of packaging. It had its own requirements for how it was going to be handled, how it was going to be carried, put on pallets or carried with a crane or dragged along the ground. Everything was different. And so then every mode of transportation had to deal with every kind of package in a different way, very uniquely. So there's people, lots of different manual laborers to move things and handle things and stuff ships and pack them up and then take them off the ships. And the packages would sit on the docks or sit in holding warehouses while it was waiting to be bundled and moved. And it was just a very complex setup. Anybody trying to ship from some packaged goods from one point to another actually had to have contractual relationships with every single vendor along the way for every mode of transportation going from end to end, right? You couldn't even, think of it as one continuous thing. So they also had the same matrix from hell, where every combination of thing had to be dealt with individually. So you have this huge explosion of complexity to work with. Costs were high, shipping was extremely slow. Some things just couldn't be shipped because they would perish before they got to the other end. It was just too expensive to ship something across the world because the cost of the product wasn't worth the shipping cost. So in the shipping industry, they developed what's called the intermodal shipping container. We see these now, especially in towns like Antwerp on the docks. These containers are everywhere. They're all over the world. They're all pretty much the same. Anybody who wants to ship something just fills up a container. It doesn't matter what's in it. You deliver that to the shipper. They can take it from anywhere to anywhere. It can be on trucks. It can be on trains. Put on ships loaded with cranes very rapidly. The fast-moving cranes can unload and unload ships in just a few hours. And you don't care how it gets there. And in fact, if you ship something from point A to point B and that's your business, it could change routes depending on costs, any given day, any given week. So it's just part of the problem that you don't have to think about it anymore. And there's an interesting side note. So this book talks about the shipping container, the real one, not the Docker container. And it talks about the history of that and how it came about. And so one might think that somebody invented this container and everybody said, aha, this is the way to do it. And it was just this big bang invention that everybody jumped on. Or maybe you might think it was a committee that got together and said, we need to develop shipping containers so that we can solve this problem. Let's get a bunch of people together and solve it and get agreement on it and standardize on all the sizes. But what it really was one guy pretty much wanted to solve this for his business. He didn't really care, but he actually wanted to beat all the competition. So he developed this container sort of in an ad hoc way for his company to deliver a shipping service end to end. He was actually in the trucking business and wanted to enter the shipping business so he could take care of the whole end-to-end process. And as that evolved, the competition started copying him to keep up. And the whole thing just took off, eventually exploded in the 60s and 70s, just because it was obvious that was such a cheaper way to deliver and ship things that it just blew up and became a de facto standard. That there's the parallel in our world with the Docker containers too. So Docker is the shipping container system for our code, as in the intermodal shipping containers are for physical goods. It's an engine that allows us to package up all of our applications, binaries, libraries, config files, everything we need to run our app into a container that can then be treated in a very interchangeable way. So we don't care what's in the container at that point. And then the tools we use to deliver and deploy can then just deal with one kind of unit of thing. So just at that point, when you're delivering it, it's just a container. You don't care what's in it. And when you're building stuff, you don't really care where it's going to go. You just know you're going to put your stuff in the container. And now the matrix from hell is also eliminated with the Docker container, where the same thing is we load stuff in, they go in the container. We deliver things, we deliver containers. That's all we need to worry about. So if you're going to add a new kind of application build, basically we just have to figure out how to put our new application into a container. And we'll get the multiplication effect of every piece of hardware deployment system that's already been put in place. Someone might say that, well, how is this different than virtualization? We already have VMs. We can already make machine images. We can use VMware and replicate machine images and run the same image that was set up on multiple machines. And in AWS, we have IDEs that we can create, which have a whole machine image with all the apps on the machine that you want to run, and you can auto-scale that and run many, many copies of your application on machines, and sort of in the way that Netflix does with their AWS tools. Just launching from IDEs and running sort of up. You have a package, you have a container. There's a couple limitations with virtualization that are important to consider. One of them is that they're fairly inefficient as far as size goes. So you end up with pretty much an entire operating system in every image, regardless of how big your app is. You're going to have an entire operating system sitting in that image, probably taking up a whole virtual machine that's sliced up in a given size. So like in Amazon, you're going to say, oh, I need an M3 medium because that's how much RAM I need, but you're going to take up that whole slot of the machine. And also virtualization has overhead of just actual runtime overhead. So there's some 5 to 10% of the machine's resources are consumed just by the hypervisor switching in and out between the different guest OSs. So you're going to lose the performance of your metal. So if you're building your own data center and you're trying to figure out how to automate things and make it more efficient, you're going to lose some of that, any kind of efficiency you gain by adding the virtualization on top. In the case of containerization, we're sharing most of that overhead. So we're running Linux. So in this case, Docker requires Linux. And it's going to share the host OS completely. So we call the basic Linux that's running on the box is going to be the host OS. It's got a particular kernel. It's got to be a fairly modern kernel for Docker. I forget the exact numbers now, but one of the fairly modern ones within the last year or so. And then the containers, when they run on top, so Linux containers, are going to be basically a process group that runs in some isolation. It will actually share the same kernel. So you're not bringing in a whole new OS, you're not bringing in a whole new drivers, you're not having to do virtualized, para-virtualized, or hardware virtualized driver interfaces or anything. It's just, now that we got the kernel that's shared, it's already knows how to talk to the devices. We're just putting different process groups on top of that, sharing the kernel. And we can also build our container images to be as efficient as we need to, so they just have what they need in their package. So they can be quite lean. And also, because we're talking directly to the kernel, we don't have the virtualization overhead of context switching. So there's basically zero overhead in putting your regular processes into Docker and running them in a container. So if you're thinking that maybe there's a tiny overhead, but there usually is none at all. And actually some tests that people have run have come back with surprising results that a lot of things actually run faster in a container. Because when you have multiple processes in a process group, Linux kernel can often context switch between those faster when they're all grouped together in a process group.
I got a question.
Yeah, go ahead.
Is there anything that you lose using containerization versus virtualization? I mean, there's got to be a trade-off.
Right, okay, so regarding trade-offs between going the other way, what do you lose going from virtualization to containerization? You do lose some isolation and security. So in the world of virtualization, the OS is a really very, very difficult, maybe impossible to get to the other guest OSs on the machine. So you see public clouds are sharing hardware resources with virtualization. The different clients, the different companies that are running their apps in the guest OSs don't know that they're sharing the machine. That's great. In the Docker world, security is something that they're thinking about and they're worried about. I mean, it's something they're working on. And this is not just Docker too, it's just general Linux containerization and the kernel level. What are the abilities there to truly isolate and properly protect all of the different process groups that are running on the kernel? So right now, I don't think it would be a reasonable solution to run in like a public cloud with containerization. So that's not really the main use case at this point. But in your own data center or even in the public cloud, if you own the whole machine, the whole virtual machine, and then you're going to put Docker on top of that, you can use Docker to share your piece, your virtual OS more efficiently, just for slicing things up. But you just wouldn't want to co-locate with other untrusted code. Also, I forgot to mention earlier, please feel free to ask questions during. I'm mostly worried about my talk actually going too fast. I'll have a tendency to just whip through stuff, but definitely stop me and ask questions if I skip over something that you think I should have covered, or you just have questions on your own. So here's another way of looking at the weight and size considerations and trade-offs. And in the Docker world also, the way it uses images, it's able to share a lot of the binary, sort of the file system image snapshots between different apps or different revisions of an app, so that with its copy on write features, which I'll go into a little bit farther through the slides, the delivery of the incremental differences can be very, very small. So the Docker images and deltas can be very, very small. So a little bit of a history segue for a moment. Google was the first to really start to play around with containers, and that process groups, or C groups they're called now, control groups, and resource isolation. And this is how Google does their big Borg kind of Omega data center management. So they run everything they do is in Linux containers. And so they added these Linux kernel features around 2007. Other projects have been using technology like this. So like Mesos is an Apache project which uses Linux containers to manage distributed clustering. And Twitter uses that for all of their large infrastructure. But they were just kernel features, and there were some standard libraries, like the LXC libraries, that people were using to talk to the kernel and build big things on top of it. But it wasn't until Docker came around early last year and put together a complete tool. So in addition to the C groups and namespaces features that are available in the Linux kernel, they added a virtual file system, which they use just AUFS, which is available as well. I mean, they didn't invent that either. But they put it all together into a package that then allowed you to create container images, manipulate containers, execute containers, and basically a complete toolkit in one program that you could use to do everything. And the container format was standardized and had a lot of nice metadata on it so that you could share containers and deploy them around very safely and efficiently. And so this sort of one-stop tool that was super easy to use, super easy to work with, allowed things to become so interchangeable that it was sort of the Docker revolution. It was like the thing that just finally pushed us over that inflection point where everybody that was tinkering around with this whole work with Linux containers kind of looked at that and just said, aha, look, this is it. It's sort of, they were the little startup company that was the Switzerland of this whole container revolution that got things going. So all the big guys jumped on it and are supporting it. So it just went from nothing. Like they were tinkering with it last spring. People started to really look at it last summer, fall time. And then by June, they were at 1.0, and everybody who was involved in this space had endorsed it. So that's a pretty impressive ramp up from something that was a little side project to basically took over the company. So the .cloud company, which was the PaaS company, is now Docker.com. And this is all they do, basically. So I don't know, I just want to repeat some of these things again. Sounds cool, it's good stuff, but what's the big deal about Docker? Why should I care about it? And I think one of the real benefits is that it's a great separation of concerns. The developers worry about their build automation, putting together their application, what are the libraries you need, what kind of configuration information do you need to go in there, what versions of the libraries do I need for what version of my app, for this, this release. So everything that you think about when you're putting together your CI to get your stuff out there, you can put that into your Docker container, right? So make Docker your final deployment artifact. Instead of having, war and a bunch of config files and a chef cookbook or a bunch of shell scripts or a big README that tells somebody how to install it, you just put it in a Docker container. You're done. That's the deployable that everybody can work with. And then however you're going to deploy it. Maybe it's still your team doing the deployment, or maybe there's a operations team or DevOps guys, or maybe you've got different teams depending on where it's going. You might have partners that don't have to deal with it, or customers, or the cloud guys do half of it and the data center guys do another half of it. But you've got a common thing that everybody knows how to then deploy and work with. There's a couple of, I think, very interesting and cool attributes of a Docker container that are unique to deployment artifacts or just kind of deployable artifacts in general. So one is they're complete. So everything that your application needs can be put into the container. So all the binaries, libraries, config, general config, that's going to be shared across whatever environments you're going to deploy. Anything, everything will be in the container. So it doesn't have to have anything added to it afterwards. It's also small, in that sort of in contrast to something like an AMI, which will be a whole machine image and is probably 10 gigabytes in size. This is only the bits that you actually need to run your app. So it's not things that are already on the host. It's also not all of the operating system packaged up into a container just because that was easy. It's really easy to make a container with just enough of the Linux support libraries that your application is going to need. If you're Java, you probably want to put the Java JVM into your container so that you know you have the right version of it. But you can just put in the JRE instead of the whole JDK. You don't need the whole thing, right? And you put in the right version of it. You put in whatever other tools. If you want Tomcat in there, you can put it in there. But you bundle just exactly what you need. It's also immutable, and this is really important. The contents of a particular Docker image can never change. It's part of it. It's the reason is you sort of when you make an image, it's always addressed. Its actual sort of physical name is the hash of its contents. So yeah, that can never change. If you need to adjust the container at all, you rebuild it in effect. So you always know that when you deploy something with a particular hash, no matter where you've deployed it anywhere in the world, you know that that version is the same version that I built on my machine and tested. It went through QA, it went through load test, acceptance test. Now it's in production. I can trace it all the way through. I know exactly. Nobody's mucked with the bits inside the box. It's universal. So I know that this container can run on any Linux host. If I'm running Ubuntu in the cloud, and I can drop my container on that. They're running Cent 7 in the data center. I can put my container on that. That's all fine. Partners are running, Fedora. Okay, it doesn't really matter what the host OS is, what libraries they're running, what tools they have on the host. We don't care. As long as the kernel is modern, we can run our containers on there. They're not going to interact with anything on the host. So that's really nice too. And it allows some nice decoupling between the evolution of what you're putting into your container, what tools and libraries your app needs, and what kind of host OS environment that the operation guys want to maintain. They can update from Cent 6 to Cent 7, makes their life easier, and the containers still run the same way. And the fact is, sort of another interesting one that is pretty unique with Docker is the container itself is actually deployable. So when you run it, you basically tell Docker, I want to run this image. Docker pulls down all the bits, creates a container from the image, and it runs it. You don't have to untar it, install it, run scripts to put it into a state where it's ready to run and then run it or then uninstall it or anything. It's just there's a cache of the images, they get run, they're just run in place in effect. And Docker manages the garbage collection of the temp files and everything for you automatically. It's all part of its command line API, so it's really easy to work with. So another side benefit is that because the Docker images are easy to create, they're also easy to share. And the Docker guys have created a public hub at hub.docker.com, which is sort of the GitHub for the Docker world. So this is where they expect a lot of people to come together and share sort of common practice in packaging up things that are already open source. So if you go there and look around, you can kind of browse around and look at things there. So pretty much everything that you might have thought to go find an RPM or a Debian for, or go to GitHub and get an install script for it to go put together anything, any kind of database or queuing system, anything that you would use in the open source world, There's probably a Docker container for it already, and you can just run it. So any questions on this so far? No? Okay.
What's stored there? Is this the recipe or is this binaries?
So yeah, so what's stored at this location, it's both the recipes and the binary. So there will be, we'll talk a little bit later in the slides about the registry, which is sort of the repository. So the binaries are there. So you can go and grab and download the binaries. For almost all Docker container images, there's also the recipe. Because you kind of want to know what's in the box if you don't trust somebody. I mean, there could be commercial containers that may be available at some point in time. There's probably going to be a business model around that where people can sell you their product in a container, and you could pay a licensing fee or rental or subscription fee, and maybe they want to keep it secret. That's doable. There's some commercial firewalls and things that people do buy, but generally the things that are on the public Docker Hub are going to be things that are also going to have their source code available as well. So here's the script. You can rebuild your own copy of it. Here's the bits if you want to just grab them, and that's what makes it really easy to just grab stuff from the Docker command line and say, oh, just run it and see how it works. I'm going to try it out. But you may find, I didn't like the way they did this. I think they should have used this version of Java instead of that one, so I'm going to patch up their build file and just do my own version of it. That's also really easy. So the first thing we'll talk about is how to get Docker. If you want to play with Docker, you got to go get it. So docker.com, that's really obvious. That's the place to go find out all about it. They have a ton of information there. Their website's always been good, but it's continually getting better. The current version is Docker 1.3, 1.31. Docker itself has to run on Linux, the actual engine, and your containers run on Linux. So it requires a 64-bit Linux. If you're currently using, let's get an idea of how many people develop on Linux directly, like on their laptops and desktops. Oh, a pretty good amount. How about how many people are developing on Mac OS? That's a lot. Okay, that's good. And how many on Windows? Oh, still quite a few. Okay, that's a good mix. Probably some people raise their hand more than once. That's fine. So Docker itself will have to run on Linux. So the containers are going to be Linux processes. So you'll need a Linux available somewhere, right? So if you're already running any of these distros, you're all set. You just use them. One of the models I use my Mac a lot, and I have machines running in AWS all the time, and I just go and tell them to do stuff. So I'm running Docker there and Docker here. But there's also ways of running Docker on your Mac and on your Windows machine. So on the Mac, there's a tool called boot to Docker, and that's absolutely what you want to get and use that. It started out being kind of a shell script thing that was pretty good. It's definitely worth the effort. Once you got it working, it was great. Now it's like on the Mac, it's a standard Mac install. You just run the installer and everything's in, you're done, right? So it's so easy. You also have the option of using brew. So if you're using homebrew on your Mac, you can use, there's a Docker installation from homebrew. That you might want if you're playing with lots of versions of Docker at the same time and you want to flip around between them. But if your main goal is just to play with Docker and develop on Docker and the current version is what you want, then just grab boot to Docker, because that'll solve all your problems. So what it actually does, boot to Docker installs, I don't know if it installs VirtualBox, but it needs VirtualBox. I can't remember. I already had VirtualBox, so it was already there. But you'll need VirtualBox or I think any of the VMwares, and it will use Vagrant to drive VirtualBox, and it will bring down its own little tiny Linux distro that has Docker in it. And it will just configure a VirtualBox environment automatically with all the ports and all of the networking all set up exactly right, and launch that for you. And it takes care of managing it for you, turn it on, turn it off. It's just sort of a nice wrapper around Vagrant to just make everything work magically for you. Now the cool thing too, on the Mac at least, is that the Docker itself is written in Go. It's very portable, the app. And the daemon that does all the work and the client that you actually type the commands into, the command line client, are the same binary. So you can compile them for any platform. So on the Mac, you can run your Docker command line client on your Mac. So you can be doing your builds and make this and do that and run Docker. And it will talk to the Docker inside the virtual machine automatically for you. So I have some pictures of that going forward. Now, in Windows, boot to Docker is not quite as full-featured, but I think they're working very hard to catch it up. The last version I saw was a couple months ago. Some of the other guys on my team are developing on Windows, and it did most of the same things that the Mac version did. It got it all installed. It got the virtual machine running. It got everything hooked up. But it let you work with the Linux inside and work with Docker inside there, but it wouldn't actually let you run the Docker command line directly on Windows. So I'm not sure why. There could be some non-compatible Windows bits in the Docker command line at this point. So, but it is easy to SSH into the container using boot to Docker. So I think that's what a lot of the Windows guys do. So using the Mac version. So all of the demos I'll be running will be Mac oriented. Most of the things won't really matter, but just to give you the context. There's a picture I stole. It's a nice picture. I've drawn this basic diagram on whiteboard so many times. I just find this, get a good picture of it. This kind of gives you context. It's easy to get lost in the inception of, I got a container and a VM in a container. Wait, no, it's a VM in a container. And so this will give you a good picture of how it all goes. You get your Mac on the outside or your Windows box. Boot to Docker then comes up and creates a VM that is running a TC Linux inside of VirtualBox. And then when you run Docker inside of that, it's going to create containers, and those are running inside of that one. So there's some command line tools we can use to go in and play around with these and look at all this stuff. But this gives you some context about when you're looking at the commands and outputs, especially when you're thinking about port mapping. It's like, okay, I have to map from here to here to here to here. This is a good little diagram to have in your mind when you're thinking about those things. So any questions so far on that? No. So Docker communicates between the client and the daemon with a REST API. So it's just JSON over REST. The default, if you run on a Linux box and they're both running on the same box, is a Unix pipe. And so it doesn't really need to worry about security. But if you run it over HTTP, over a TCP pipe, it will default now. In the new version, it defaults to turning on TLS. In the past, it was just in the clear, and that was fine. It was really easy to play around with stuff. But now it will start defaulting to turning on TLS. And so if you want to keep that, I mean, if you're just developing and you're using boot to Docker and testing stuff out, it's fine to just leave it on the default, because boot to Docker will take care of your certs for you. That's really nice. But if you want to turn it off, you can switch it to clear. There's just a config file. You can go down inside the VM and turn on a switch and say, I don't want TLS. This lets you do some fun things that I can show you. Lets you snoop on the traffic a little bit more easily. So that's a nice little hint. I had to figure that out when we switched to 1.3. And this is what the command line ends up. So when the daemon runs, it gets run as a daemon. And you can see it's listening on 2 ports. So the -H there with the Unix that's its local Unix port, and the TCP it's listening on a clear port. On 2375 is the port that's been assigned officially for Docker. And then on the host side, you just set up so this is on the Mac side that you're talking to the daemon. You tell it which address and port. So you're just going straight to it. And in the case of TLS, you got a lot of certs. And it's a good thing boot to Docker takes care of it for you, because this is something that you could spend a lot of time messing with if it didn't do it right the first time. Now, if you're dealing with Docker in like a large-scale data center deployment and you want TLS, you're probably going to want TLS if you're doing Docker over the wire. You'll have to figure out how to manage those certs yourself. So boot to Docker also sets up their VirtualBox networking for you automatically. So it sets up a local logical network called VBoxNet2, and that's mapped down into the local Linux VM. So in my examples, I'm not sure if it always uses the same addresses or just in my case, but this is the address it came up with. It's just a local 192 address, so that maps down into the VM. So I'm going to start to play around with it. I'll show you some of it working. Let me see how this green switchy stuff is going to go. There we go. Is that too small? Can you guys see that okay? Yeah? Okay. So boot to Docker is a command line tool. I think it's written in Go now. It used to be a shell script. You can run it. It can check the status of our VM. Okay, it's powered off. Okay, no problem. Let's power it on. Up. So starting up. And it's just basically talking to Vagrant and starting VirtualBox. But it's also checking to making sure everything is okay. When it comes up, it'll make sure the Docker daemon is running inside the container. It'll make sure your environment variables are always set up right. So it says, yep, environment's already set. In my case, I'm running just clear in the clear, so it set up my Docker host for me. So now we can do Docker things. So I could say, like Docker version. Aha. So client version. So that's the Docker that's running on my Mac directly, is 1.3. All the versions of the libraries and things. And then you can also see here the server version 1.3. So that's the server, that's the daemon inside of the container and down inside of the virtual machine. And then there's API versions and things as well. We can also, let's see what else is interesting. Info. Boot to Docker can tell us a lot about the virtual machine that's put together, what ports it's on. Oh, we can find out what IP address we need to talk to the virtual machine on. So certain things like that you can play with. I mean, mostly you'll just do up and down when you're done. And when you're all done, you can just say down or off, and you can force restart it. Things sometimes get weird, and you can restart it. But otherwise, it's just a tool to get your environment going. It's really great. Yeah, starting, stopping, suspending. You do kind of want to shut it off if you're not going to be using it, because having the VM running will suck up some of your CPU all the time. So if you're walking around with your laptop unplugged and you're wondering why your battery only lasts an hour, well, it's maybe you left your VM running. There's one interesting one here, though. Okay, let's do this. So when I ran Docker here, so I said Docker version. I'm running the Docker on my Mac, and it's talking to the Docker inside the VM. Everything looks great. I could do a few other things. I think until Docker info, it tells me all the things going on about the Docker that's inside the VM. There's one more very useful command in boot to Docker called SSH. So it's actually SSHs me down into the VM. So now I'm inside. I'm not on my Mac anymore. I'm in the TC Linux, the tiny Linux that's inside of the VM. So I can see where I am down in home Docker. Who am I? I'm Docker. Now if I run like Docker version, things kind of look the same, but I'm running now in the Linux version entirely. So this, if you have the inception picture of the nested VM inside the VM, now I'm running things down inside of here. And for the most part, running Docker here is going to run the command line talking to the local daemon inside the VM. Will be the same as running it on the outside. But sometimes you need to get into the Linux itself and look around at stuff. I mean, you can then like poke around and look at like var, oops. Where's the Docker stuff? Yeah, you could poke around like what Docker is doing, and it's fine. If you just want to get down into the nuts and bolts, so you're down in there, you can do that. Okay, let's come back to the Mac. And talk a little bit more about the Docker daemon. So here's kind of a good general diagram about how Docker is working in relationship between the client that's executing your command line utilities, the Docker daemon, which is run on the host, and the Docker registry, which is managing all the images. Now, Oftentimes, you're running the client, the command line client, on the same machine as you're running the daemon. That's pretty common. So if you're running, on your Linux development environment, they're on the same machine, but they don't have to be. So they could be on a separate machine. And all the commands you do, even when you're running on the same machine, everything you do on the command line is going to turn into a JSON request and get sent over. A REST call will be made to the daemon. The daemon will execute the commands, do whatever it's going to do, and then return some kind of result back. So it's always this sort of REST-based command line and service response going on, even when they're local, which is really nice because it makes it very consistent and very easy to sort of understand what the behavior of the engine is. So all the commands you're doing, like pull and run, and all the Docker commands we'll get into in a little while, are going to be sent over the wire that way. All the containers are going to run on the host. Images, so the registry, as I mentioned earlier, the registry is effectively this is what the Docker guys call their repository manager. It's the registration of images, and it's the storage of the image bits are on the registry. So when you do something like a Docker pull, you say, I want to pull an image, it'll tell the daemon to go out to the registry, find the images, pull the bits down in different pieces, store them locally, and then they're cached locally in the Docker environment on that host machine. It is interesting that Docker guys chose to just make the binary for the command line the same as the service, the daemon. Makes things really easy because to run the daemon, you just tell the command line to go into daemon mode. It's very convenient. There's only one binary to distribute. In environments like boot to Docker, the VM, that when it comes up, starts up the daemon as one of the init processes, so it just comes up. If you're running it locally on your a local Linux development environment, you run Docker when you need to run it. You can just start it and stop it whenever you want to. And it's the guy, as I said before, doing all the work. Initially, the Docker guys started out using the liblxc, which was an existing Linux containerization library, which then in turn talked to the kernel to take care of the C groups for creating containers and the control groups for the containers and the namespaces when it created the Linux containers. But they've since then found limitations in the LXC library and have created their own, which is now open sourced and is being worked on by a lot of people. So that is now called libcontainer. So that's a key. If you're interested in following along that project, it's up on GitHub. There's a lot of other, I think the Mesos guys are contributing and the Google guys, and as well as the Docker guys. So there's a lot of innovation going into there to extend what the library can do and how much of the work it does on behalf of the tools that are going to want to talk to the Linux kernel. So in addition to dealing with the process control, Docker also manages networking for the application. So it creates and manages a NAT that lets the containers talk to each other and talk to the outside world. And it also allows and can control volume mounting. So we'll get into that in a little bit farther down. So here's a big picture. I don't expect anybody to follow it along completely, but this is kind of a block diagram of the internal architecture of the daemon. And you can see the main thing is, it's a REST service on top. It's got parses all the commands that are sent in JSON, executes little jobs inside of an engine environment internally, and then has different drivers for talking to different things. So I'm dealing with for instance, like the networking bridge. What kind of networking mode are we in? All of that. What kind of file system are we on top of? The virtual file system that it uses. All the different things like that are pluggable. So the initial implementation of Docker was somewhat monolithic. They were built on AUFS, and that's kind of what it relied on. But over the last year, starting a year ago, they started to break it up. They made it very, very pluggable and pushed stuff down into libcontainer that made sense. They made other things more pluggable, like the graph driver. You see AUFS right there, but they also support BetterFS and a couple others as well now. So, and I think AUFS is not even the default anymore. But that does make it more extensible and more configurable, and they're even doing a bunch more of that going forward, so that you can have dynamic extensions to Docker. So you can plug in some of your own features here and there if you want to customize certain like setup, like when containers are started, you should be able to hook into that if you wanted to. So any more questions on the daemon? Go into that. No.
And the security on the daemon?
The security on the daemon. Yeah, so you talk to the daemon with JSON over REST, but the default now and the sort of the recommended is to use TLS.
I mean authentication.
Oh, authentication. Between the client and the daemon, there is really, I don't think there's authentication. Yeah, that's something that, so the Docker guys in the last few releases are really starting to focus on security. It was on their list of things they knew that they needed to do. I think they're initially focusing on security sort of from the respect of trustability of the images. So signing of images and who created the images and following kind of an authority chain as the images are layered up. And I think they're working in that area first. The channel security is sort of done pretty well already now with the TLS and the certs that you can install. Authentication for getting images is in place. So when you're requesting images from the registry, you can make sure that you can have access control there. But yeah, sort of any kind of authentication or even like nothing in the area of finer grain authorization control, like even somebody run read access but not write access. I don't think that's there yet. But I wouldn't be surprised if it was on the short-term roadmap. So it's a HTTP JSON over REST API. And if you're on the local Unix socket, it's just going to be the JSON as well, same basic API. It's really nice. There's a nice online reference. They rev it every so often, add new things to it, actually, and there's a bunch of commands that I hadn't seen until I started putting this demo together, so I'm going to have to go back and play around with pausing and unpausing of containers. Is pretty new. So let's play with the daemon itself. So I use a little utility called httpy. I think that's how you say it. Whoops. I can't copy without. Oh. Okay. Sorry, this worked when I was practicing it at home. So let me see. Boot to Docker status. What are we doing right now? Okay, we're running. So I can make this is HTTPy is basically curl with pretty command line and color coding output. Just makes things nicer to work with. So I basically now made just an HTTP GET call to the daemon itself, which is listening on port 2375 down inside. So I'm running on my Mac. I'm talking to the daemon inside the Linux. I've asked it what version is it. So it gives me back a JSON blob, tells me the version. I can ask it some more info about what's going on. It'll tell me all about how many containers are running, what driver for the disk, for the virtual file system is it running, how many images, 153 images are available right now that I've already got preloaded. Number of different things that you can see, what versions of everything. What are some other good things to run? Ping. It's okay. Yeah, that's just the very easiest way to find out if you can see it or not. Now there's an images command. This one's very interesting. How do I do it? JSON. Yeah, all equals 0. And we'll go into some more detail about images, but I just want to get a basic. Let's look at something. Whoops. There we go. So it gave me back a big array of objects that describe every image that I have available in that Docker environment in the VM. So it gives me a creation date, The image IDs, as I mentioned a bit earlier, they're all basically like a SHA-256 hash of the bits of the image, so they're immutable. So that identity of the image is really its canonical identity. If I talk about this particular image here, dockers.tf Riot Games, .d scout, that could move around. That's kind of a logical name. That's a sort of repository tag. But the physical name, that's the hash, will never ever change. So if I want to make sure I've recorded what was deployed in production on this day at this time, I can record the hashes and I know everything at that point. But most of the time when you're just playing with stuff, you just care about the logical name. And so there is then a mapping that's done in the registry for you. Images can have tags, so you can see there's an alpha, versioning tags, or latest, or alpha, or 0.5. And virtual size, things like that. That's effectively the same. So I've run this as like a request to the daemon to tell me about images. That's really the same as if I had said Docker images. Same information. So the Docker command line is forming a JSON, a REST API request. It's getting back that same response in JSON and then displaying it in the command line in a table. So it's doing the exact same thing. These are fun to play with because at some point, if you want to write your own tool, say, I need to know the image, I need to find out from Docker, the total sum of all the sizes of certain kinds of images, and the command line is not easy to use, well, fine, just write your own little app, a Python script or something that can make the REST call, grab the data, do what you want with it. It's super easy. We'll talk a bit about images and containers. I've used those interchangeably, and oftentimes we do in the Docker world, but it's kind of good to have the right terms, to understand what the exact terms mean, so that when you do choose to misuse it, you still know what you're talking about. It's so easy to think of the container as the thing with all the bits. Like the thing I'm shipping around is you might think of it as the container, because that's in the physical world, the shipping container carries the stuff, the bits, right? But in the Docker world, the container term came from the Linux containers that are containing the processes. So the Docker container in our world here is the processes that are running. So it's the running container or the stopped container, but it's the thing that represents the instance of this container on one particular machine. And the bits that are copied, that are made from the container, that can be used to create a new container, and that can be transmitted around the world, that's called the image. So that's the Docker image. And then a registry is the registry of images. So that's where you store the images off. So just to make sure we have the names clear. Here's kind of a pretty good diagram of how they interrelate with each other, how they interact with each other. So oftentimes you can make Docker images, and we'll go into some of these Docker files. The most common way to make a Docker image is with a Docker file. It's kind of like a very simple, very, very simple make file. It's not even, there's no conditionals, it's very linear. It just says what you want to put in the container. It's almost like a manifest of how to make a container. When you run a Docker build, that will tell the Docker engine you want to make something. It will start a container from a base image, run whatever instructions you tell it you want, and then save off the resulting container that was created into a new image. And then it will push that image, if you want to, you can then push it to a registry. So this would be kind of a workflow that you might have, if you had a Jenkins job that was building your app for deployment. You could run this flow in your CI. And I can show some more. Let's go down and show some more Docker commands around images. So I can go into some more detail here on all the images that I've got. So you can see some of them have different length and names, and some of them have no names at all. The case like the first one, so cquinn web hello go. That was an image I made last week when I was putting this demo together. It's in the repository. Let's see, trying to get the names right. It's not in any particular repository. It's only local. I haven't pushed it anywhere, so it has no repository part of the tag on it. It's in the repo called. Okay, got it. So they do use the names funny. The username is Quinn. That's me, and the repo is called web hello go. And so you think of that then that's basically the image name. And the tag on it is effectively a version tag, is called latest. So a lot of this is actually modeled, the naming, the terminology around on the image names and the tags and the IDs is actually more like Git than it is like a traditional binary repository. So they're trying to think of modeling delta changes to a particular artifact as very similar to just doing a commit on Git and just getting a little incremental delta with all of those Git endpoints having a hash. That's their actual real identity. So it's the same kind of idea. I built a bunch of containers and never gave them names, so they just have their hashes. So that's what all the nuns are. There's a few other ones here, like, okay, this one's Scout, Alpha, 01. So that one has a 3-part name. So the first part being dockers.tf riotgames.com. That's our registry at work at Riot Games internally. My team that I'm on is called DAT, so we have a username in the registry called DATD, which sort of holds all of our Docker stuff. And then Scout is the little test Scout program that we use to test our cluster stuff. So it goes out and scouts around for us. Some of these other ones are actually public images. So the Google CAdvisor image, its username part is Google. The repo or the image is CAdvisor. It doesn't have a repository. In this case, it's because it came from the public repository. So I just did a Docker pull to go get it. So there's the other commands you can do are things like, so Docker pull. If I said I want to go get Google CAdvisor, it will go out to the public one, ask for its actual the hash to get the real hash, and then check all the layers and start pulling them down. So in this case, it went through, found out everything, went to go get all the layers, realized it has all the layers, and everything just went really fast. So we've already got it, so that's great. I'm really glad it didn't go out and start downloading 100 megabytes of stuff. Some of these other ones like BusyBox. So BusyBox is a great base image that you can use for small apps. There's a couple versions of it. And a few others here like Orchard Up. So I'll show those off in demos going forward. I should mention tag. So once you have an image, you can create it, you can test it, and you can leave it anonymous just as its hash. And when you're ready to do something with it, you can give it a tag. So let's say there's an image we have here called 91DDD, this image. I can tag it. We can say, oh, Docker help tag. What's that syntax look like? So we do Docker tag. The image is going to be, so with respect to the hashes, the actual canonical hash is the full 256 bits. That's the real name. But just like Git, you can refer to it with the first few characters of the hash. So you can grab just like, I guess that's about 20 of them. So in most of the UI, the APIs will accept a short hash, and the columnar output will often use the short hash unless you ask for the full hash. So that usually is good enough for everything. And then I can give it a username. We can call it Quinn, delete me. And now I've just given a name to that particular image. And I can go and look at all the images now, and we see it's here. That one there is now called Quinn, delete me. And I can play around. So you can give it another one. I can say delete me too. And now I have two logical tags that are pointing to the same image. You can see both of those delete me's now point to the same one, 91DD. So you can have aliases. Oftentimes that's used for, you wouldn't use it for repos probably so much like this, but you could use it for versions of things. So you might give something the version with a number, and then you also might tag it as latest, so that you can always refer to the latest, and you can then move the latest tag around. So sort of like tags in source control as well. So let's look into a little more detail about what images actually look like inside. I need a little more water. So Docker images are actually built in layers. Docker uses a layered virtual file system. So initially it was AUFS, and now it typically is BetterFS. But the way to think of it is, when you're building a Docker image or running the container, the bottom layer is going to be some kind of base OS that you're going to start with. And let's say it's going to be like a tiny Ubuntu, like the BusyBox Ubuntu. It's just going to be a base, kind of a tarred up image that's just kind of the boot part of the OS. That's maybe going to be, actually I can go back and show how small that one was. So like the BusyBox Ubuntu 14.4 near the bottom, 5.6 megabytes. So that's like an entire startup environment for Ubuntu with all of the glibc and all the basic stuff in etc. Most of the files are there ready to go. You can put Java on top of that. You can put Python on there if you want, but that's the minimum that will give you a pretty reasonable little Linux starting point. And that's a much tinier overhead than 10 gigabyte AMI. But it's not going to have anything off the shelf to start with. You'll have to add things to it. So if you start with that, or even like Debian, you're going to get the basic OS, but not a lot of runtime. You're probably not going to get Python or Perl or Ruby or Java or anything on there. So if you want to add those, you want to add those on top. So what you want to do is layer things on top. Let's say start with our basic OS. Let's put on some utilities that we always want to have available from our app, or shared libraries, or language runtime. And maybe in this case, we've added Apache because we want to run Apache in the container with us because we always want that to be in there. And you can add those in layers. And each layer that you add will get snapshotted off and saved as sort of an intermediate image with its own hash and everything. And they're chained together. So you can see that each one references the parent. And it goes all the way down. So if you refer to a particular image, like the Apache image there in the middle, and you say, I want to start a container with that image, it actually follows the links down to the rootmost parent, which will be the base, which has no parent. And it will load in all those and layer them on top of each other. And each of those images represents some sort of sparse graph of files. And as they're layered on top of each other, the files sort of layer on top of each other. And when you look at the resulting union file system, you see the union of all the files. All of the directories and all the files are all appear as if they're just one file system. And you can read all those files just through file system APIs. Now, when you're running a container, Docker will put one more writable file system on top. So all of the ones that are there that were referenced from the images that are immutable are always going to be immutable. But then the file system layer on the very top is the one that sort of goes with the container. So the apps in the container can write into that file system and do things. You can add files, remove files, and even kind of shadow files from the layers below or remove them. And that layer will be writable. And when you commit it, so Docker can then commit that layer to disk, that becomes a new image, and that references its parent. So the process of creating images is just you create a container on top of a base image, put some files in it, and then save it. And then create a container with that and put some files in it and save it. So you can just continually stack up these layers of virtual files to build up what you want. Now, if you decide that 5 layers up, you have a version of Apache that's obsolete, you want to replace it, you can go to its parent, find the layer you had below it, put in the new, make a new container, put a new Apache, save that. So now you've got effectively a tree or a graph of these containers that are tracking your versioning, just like you're versioning source files in Git. You can be versioning and managing all of your Docker images that way as well. I know that seems confusing, and my picture is pretty limited. Do people have questions on that? Definitely, it's good to have this visual picture of this in your head.
How to display the layers of a container.
Ah, okay. How to display the layers. Let me see. So we can pick one of these guys. So the ones that are going to be low level, okay, I'll pick one that's really, let's grab the BusyBox one because it won't have any. So we'll start with that. The inspect command in Docker will let you inspect either an image or a container. In this case, we'll look at the container. And it does have a parent. So you can see basic information, meta information about the container, who wrote it, Jerome, Petazzoni, how it gets started, the container that was used to create the image, and at the end you see its parent, 25FB. So that was the parent of that container. So then you could just sort of recursively walk up and down the tree and do that. So that will give you a lot of detail. You could step through and look at things little by little. There's also a command called, let's see, history. Oh, my command line's getting confused. That'll display it in a more concise way. So if you look at the history of which one were we looking at? The Ubuntu BusyBox. And we see that it was made in 3 steps. So it was started by grabbing a binary tarball of a distro of something that was the boot, or which could actually, 0 byte. Actually, so that's sort of the root image that has nothing in it. There's a way to start a Docker container and say, I just want it from scratch, is what you say. So you get this sort of fake parent, that's the null root, that's the bottom. And then 5 weeks ago, Jerome made these and added in different layers on top by running these different scripts to add stuff on top of those. So pretty much most of this, you can see most of this container came from the middle guy where he finally just did a big blob dump of everything on top of the container and saved it. So that's how he's managing these BusyBoxes. There's a little bit of black art in getting the bases built, and so there's a bunch of guys that are playing around with different bases and how to make them small and efficient, but not too weird that everything breaks when they run on top of it. But we can all benefit from the hard work they're doing by just grabbing and using their base images. We can look, actually, so you could look at one that's more complicated, like Scout. I gotta say, oh yeah. Yeah, I have to use the whole name. Okay. Let's clean up. There, okay. So this is more of a typical container when you're building for a final app. In our case, you can see at the bottom, you do see the BusyBox layers from Jerome and then the blob. And so there's the 5 megabytes coming from the actual OS. And then a bunch of commands which actually do make layers, but they don't actually take up any room. They're just kind of logical steps in the history. So there is a image representation that's basically just metadata and some JSON, but no payload. So those are fine. Those are all chained together. And then you can see where the files are added. So half a dozen files in there are added. In this case, there's a whole bunch of little config files. And then the 9.2 megabyte, that's the actual Go program. That's our app. That's it. So that's the whole thing. And then setting the command line to tell the container how to run the app. So each of those ends up being layers. And we can talk a bit about it. There's an art to doing your containers so they don't end up with a huge number of layers. And you can efficiently put together your CI so that you layer up things in a nice, neat, and concise way so they don't bloat and get too big. I think there is a limit, maybe 30 to 40 before Docker has an absolute top-end cap before it can't deal with any more layers. It might depend on which file system driver it's working on. But it's good practice to keep things tight. Like the steps where I put my config files in, they're just being added one by one. There's some better ways we could have done that. We could have untarred a package of config files. That would have been one step.
Can you actually browse a union file system?
You can. Remind me later when we run the first demo, and I can do the browsing of it. Yes?
Is this image committed to the dev environment?
Oh, so where is the image committed?
Is it linked? Can it be only used on the dev environment?
So can the image only be used on the dev environment? This particular one, you could see because it has a registry name, dockers.tf.riotgames.com. That came from our registry at work. You can choose, when you've created a Docker image for deployment, it's pretty much, you're going to want to use the exact same bits for dev, test, prod, right? You're not going to want to rebuild it. And you have the benefit then of knowing that you're running in production the same thing you've tested. So how you manage whether or not you want something to be allowed to go into dev, or to be promoted from dev to test to prod, there's different ways you could do that in your environment. You can have different registries and physically copy things. You could also have tags where maybe you only will run things in prod that have been tagged prod. So you can play around with things like that. In this case, Scout, we're running CI. We have Jenkins jobs that are pushing our Scout tool out into our registry all the time. It's not a production-facing app. Customers aren't hitting it. It's just the way we use. It's a tool we use to test all of our other tools. It's our sample app, in effect, our Hello World. But it's important to us because everything else in our CI would break if that didn't work. So that should be that. So any more questions on the layers and of the images? Can the layers be merged? People have asked for that feature, and I don't think there's a tool that can do that yet. It would be nice to be able to just go and, just squash them. But no, there isn't currently a way. Normally you would just sort of go back. You also do want your images to be built from a CI system that allows you to reproduce them very easily. So if you have images where you've built them and they have too many layers, you could just go back and sort of audit how you're doing the builds and update your build files and then build them again. So that's sort of what that's the best practice at this point. But it would be nice to be able to squash things. There's some tricks that you can do in your Docker file that will make things in less layers. So as I mentioned, your containers are always going to start with, all your images are going to start with some kind of base. And these are good bases that I would recommend to play with. If you want like a full, normal Linux, Debian is a really good choice. It's about 120 megs. Once you've got your app running and you just want it small, the BusyBox, especially the Ubuntu BusyBox, is a really good choice. That's the one I showed you that was 5 megs. That's really, really tiny. It just leaves off a lot of the normal Linux binaries, because when you're running your app, let's say you're running your Java app, unless you're running spawn commands from inside your app, you don't care whether or not there happens to be an ls or a cat or a ps binary running on the image with you. You're never going to call it, so you don't need it in there. So let's just take all those out. So that's what the BusyBox really is. And then Ubuntu and CentOS those are a full Ubuntu, full CentOS. You can get all the versions. Any of the versions you care about, you can use those as your base. Those might be useful if you want to package up a third-party tool that really does spawn and need a whole bunch of things and it makes a lot of assumptions about its environment. You could start with that. But they're starting to get big, so I think Ubuntu CentOS are like 250 megs. And if you just sort of naively grab Ubuntu, grab like the Java JDK, you get JDK, and you get Java 7 JDK, and you just install the whole thing. You say you're going to get like up to about 700 megs pretty quickly. Things get really big and start sucking in other things. But you can instead build JRE and just grab just the parts you need, headless JRE, in fact, because you don't need all the GUI stuff when you're running on a server in a container. put that on Debian or put it even on BusyBox. You get a nice, tiny little Java runtime base in a container. So it's fun to play with. It doesn't take very long to experiment with these things. See how they work, see how big they are, see if your tools work inside of them. It's a very nice iterative process. Look, we got ahead of ourselves. So we're going to do Docker history, which we did. And that was the main takeaway from that one. Are there any more questions on this so far? Yeah.
Run an image multiple times.
Right.
So you have several containers of the same image. Does it reuse the immutable layers?
Yeah, so the question is, you can make multiple containers from one image. And the question is, does it reuse the immutable layers of the images for each of the containers? And the answer is yes. It builds a whole kind of graph with links. So yeah, you could run, let's say you run Ubuntu, I could run 50 containers with Ubuntu on my Mac. I'll have one copy each of the actual image layers, and then 50 little thin writable overlay layers, one for each container. And if they don't write anything, those will be 0 bytes, effectively, plus metadata.
If you make a new version of an image, does it make sense to reuse the layers from the first version to kind of just add another layer?
Yeah, so if you make a new image from an existing image, you have a couple of choices. You could choose to add to an existing image, add on top of it. So you would say well, I can actually show you. Actually, it'll be easier. Let me skip ahead a little bit, because right in here. So ignore this is what the demo is going to be. Okay, so here's a very simple Docker file. So this is your declarative manifest, that sort of the make file equivalent in the Docker world. You can see the first thing is always the from. So what image are we going to start from? Unless you say start from scratch, it's like a little special keyword, scratch, then you're really going to be referencing somebody else's image to start with. Other things in here like maintainer are just metadata, just fills in the metadata. The commands like add are going to tell it to add some files to my container. The command called command tells it's just, again, some more metadata that's added to the container so that when Docker runs it, it knows what to run. So the only thing that's actually going to create new things for an image is the add command. That's going to be adding our binary, our little program, to the container. So I started with BusyBox and I added to it. So if I wanted to do that again, and I wanted to change the program I put in the container, put in the image, I could go back, start with BusyBox again, and add it. And now I have a new one. That's sort of a branch. I got the old one and the new one with the same parent. Or I could say, oh wait, I forgot a config file. Let's add a config file. So I could start with the image that had my app on it already, and then add a config file to that. So it will chain, but you can choose to sort of back up, walk up the ancestry tree to a common point where you want to restart. Like you can replay history, walk up to the point where is to your starting point, and just start over again and build it again. So in this case, in my makefile, every time I build my app, I always start from BusyBox and I always put my app on it. So that's always the same starting point. Typically, you'll do this in a CI world where you kind of you will have that chain of parentage, ancestry chain, sort of well defined as part of your CI. It's just like you would be building new jars and depending on other jars and just adding the next thing by rebuilding it depending on the existing things and adding one more thing to it, the next chunk of functionality. So let me back up to the beginning of this example. So maybe I'll do a couple of these examples and then we can take a break. I think it's probably about the right amount of time. So I'm going to show you a small program called TikTok. It's written in Go. It's really small. All it does is write the standard out. Just writes TikTok. Looks like that. Since I've been working in Docker for the last year, I've started writing most of the stuff in Go. For something that's going to do really small things or command line tools or little small daemon apps that are servicing REST APIs, Go is a really good language for that. It has a very small runtime overhead, so a reasonable app is going to be about 9 megs. You can make little tiny apps that are a couple megs. They produce a binary that runs, that are self-contained. So they're really good for like deployment tools and things, because I don't have to tell somebody to install a JVM to run my command line tool. It's kind of a non-starter for some people. Or make sure you've got this version of Ruby and you install these gems and make sure they don't conflict with your system Ruby, or Python with these eggs. Okay, here's a binary, just run it. That's really nice. So we can run this program. It's not very fancy. Although it is funny, kind of going back to old school, make files. Okay, so now we have a binary called TikTok. We can run it. That's what it does. Okay. You can see the binary there. How big is this guy? So he's 1.8 megs. So that's the size of this binary. He just has standard out libraries. He didn't need much else. Not a lot of extra code to that guy, so he's very small. What else do we want to do now? Okay, so we run it on the Mac. There it is running. That's the binary. So I've run the Go to compile a binary for the Mac. So it's running with a Mac runtime bundled into it, right? So it's targeted for Intel and Mac bindings. So now we want to Dockerize it. So this is the Docker file we just saw a minute ago we were talking about. This is all the instructions we need to tell it how to make the Docker container. Well, it is the best analogy, I think, is it's a manifest. The instructions, the only thing that's sort of sequential sequential are the adds are added in order. And there's another directive called run, which will run things to be put into that, right? So you can install, you can run apt-get, things like that, to add stuff to your container. So we'll make a Docker image, okay. So that was the build. So that just now ran the complete cross-platform build to build my app for Windows, Mac, and Linux. So it did all of that. Put them down into a little subtree. I grabbed this snippet of our makefile template that we use at work for all of our apps. So I could show you the makefile. There's stuff in there that we don't even need for this sample, but are nice to have around. So we build TikTok for these different environments. So only building AMD 64 because I don't care about ARM for this exercise. But you could also build Go for ARM and all these different OSs as well. And we've also then, part of the output, you can see the steps there. The step 0, step 1, 2, 3, those are coming back from the Docker command that was run by the makefile. And it started from BusyBox, Ubuntu 14. Step 1, it created a new image with just metadata that was adding me as the maintainer. Then it added the binary, TikTok. It did some cleanup of intermediate containers just because there's certainly, I guess it does that automatically. It's got some temporary ones in between. So it does some squashing, but not as much as you might want. And then it added the command metadata to it. And then it cleaned up, and it's all done. So the final container was the C42 one. So now we can do images and look at all the images. Where is it? Oh, yeah, it's the top one. Latest Quinn TikTok about a minute ago. Yeah, so that's one we just made. And what is our instructions tell us to do? We can do a history and inspect, which is going to be, oops. Yeah, so that's basically, it looks a lot like the reverse of what the Docker file said to do. Start with the BusyBox, which was down there, the 5 megabyte one. Set some metadata, the commands, well, the maintainer, and we added the file there, which is the TikTok program. Then added the command that should be run to run the container. That's just metadata, then we're done. then we'll run it. Oh, yeah. Demo, and we'll run it. Okay. So now we can run it. So I've got, just so I wouldn't forget, I made a bunch of little shell scripts. So if you're playing around with these from the GitHub pull, there's a bunch of shell scripts to just help me remember what to run. So what we're going to do here is we're going to run, there's a Docker command called run, which actually does two things. It creates a container from an image, and so you give it the image on the right, and it will create a container from that, and then it will immediately run the container. So in theory, with the API, you can create a container and not run it, but the run command always just does them both together. The command's IT, that basically tells it, try to remember, to take input from the console and create a virtual console. So the two things to remember is that you're probably either going to want to run it -it, so run it if you want interactive command line back and forth with it. It'd be connected to the standard in, standard out of the console. Or you run a -d if you want it to demonize and run in the background. In this case, I gave it a name, TikTok, so that it's easier for us to find the containers during the demo and clean them up when we're done. So that just gives it a label when we look at the containers. So we can run it this way. So it's in the container. It's running. But how can you tell? It looks the same, doesn't it? Let's see. Do we have something figured out now? Let's do this. Let's see. So we know. Okay. It's hard to even. How can I prove to you that we're running it in? We're running the Unix version in a container in the VM on my Mac. Let me just type Docker -d. I'll probably have to clean them up. That's one way to do it. Okay, so I killed it. We can do now Docker PS. That will show us the containers. There's nothing running right now because we killed it with Control-C. If I do a PS-A, it will show me all containers. So even containers that are stopped. In this case, it says, okay, there was one running, the container ID. So the container had an ID itself, a hash. The image that it came from is listed there, see Quinn TikTok. The command that was run, which was based on the one that was built into the metadata for the container. And then it told us it exited with status 2 42 seconds ago, because that's because I Control-C'd it. So we could kill it. So we want to, if we try to run it again, it will just break because it's already there. So the dead one's still sitting there with a name called TikTok. And I tried to create a new one with the same name, but can't do it. So I had to kill it. So a lot of the commands that take identity for an image or identity for a container will accept either the hash or the logical name if there is one. So now it's gone. And if we do a PS-A, nothing. Okay, it's gone. Now we can run it again. But let's run it in the background. Docker run -d, and we'll do all the rest. Okay, it's running. So it told us about the big on hash. That's the container ID that it made. Now we can do a Docker PS. Let me clean up there. And you see it's running. It's been up 12 seconds. We can check it. It's still running. Now it's up 16 seconds. But what is it doing? How do we know? Well, if it was something that was a service, we could talk to it over the network, but this guy's not. But we can look at the logs. And we can see, boom, that's what it had output since I last asked for logs. And I can look at it again. I can do a logs-f. It's basically like tail. It's tailing standard out for us, so we can watch it. We're just sort of watching it standard out. And really, actually, probably what Docker's doing is tailing the standard out file that's down somewhere in its virtual file system under its graph, under varlib Docker. But this lets us see what's going on. And if I kill it, I mean, it's still running. I'm just not looking at its logs anymore. But it's a handy way if you have a service that's running, it's writing standard out, it's writing logs as standard out for its status. It's talking over the network. You can poke it and look at it in different places, different ways. So when we're all done with it, we can get rid of it with either stop and the container, TikTok. I can either say TikTok. Now what stop does, it sends it a SIGINT and waits. So I didn't add any signal handling to my program, so I ignored it. Program ignored us. So after 10 seconds, Docker stop gives up and then does a kill -9. So now if we look at it, PS, it's not there. PS -A, it's there. We see it exited with a -1 12 seconds ago. It got killed. So now we can RM it. Keep our VM very tidy. Whoa. Oh, I spelled it wrong. Okay. So there we go. Back to this.
Is there a way for the application running inside Docker to know which container ID it has or something like that?
Oh, that's a good question. Does the application in the container know its container ID? I'm not sure if I know the answer to that. But in general, what Docker does when it runs your container, a lot of the information about your context is passed in the environment. So there probably is. We could figure it out later on, exactly what's passed. Especially if you're starting to do some of the more advanced things like linking the network ports together. Docker will set a bunch of environment variables and pass them through to you. And we've done the same thing with our system that we're doing with Docker, is any kind of context about how your container was run, what ports and hosts that it's on, things that that might need to know, are just passed in the environment with a prefix, and it could scan those environment variables. So that's kind of the standard idiomatic way to do that kind of stuff in the Docker world. I think we're exactly half through. So why don't we do a break right now and come back in 15? Okay, I guess it's time to get going again. People are still coming in a little bit. So the next step, I'll continue on with the demo, and we'll go into a slightly more complex demo that's doing something more than command line, so we could see another feature of Docker, the network area. So here's another small program in Go. This one is going to do, it's basically a little web server. It has a couple functions. It's on 2 pages, so I'll just walk through this really quickly. It's very contrived. So I mean, you have to give it a little bit of a break. It's gonna web serve data. It's keeping a counter. It writes the counter in a text file in a directory called /data. Okay, not very sophisticated. There's no database. That's very dumb. And it's just gonna say hello and count and update the counter. And then the counter update code is here. We're just reading the file, reading the number out of the file, and then writing the number back to the file so we can count. It's very brute force and very simple. I just wanted to make it small. But what we'll then see is a couple things with the network, and we'll see some things with the file system and the volumes that are kind of interesting. Same BusyBox idea. We're just going to make our Docker container like that. Looks just like the other one. There's nothing different. So we're going to make a Docker image. So this also sample is on the hello Go. There's all the files. Most of the shell scripts are just tiny Docker commands, so I don't have to type them. Building container done. Okay. Now what are we going to do? We're going to run it. Okay. So we're going to run it. Now when we run it, we have to tell Docker about the ports. So if you remember the source code, we told the web app to listen. I didn't point it out, but there at the bottom, we're going to listen on port 8080. So the app is just going to open 8080. It's not been prioritized or configurable or anyway. It's just always going to be 8080. So it's pretty dumb. But Docker will let us adapt to that. So if I wanted to run that program and if I want to run 20 instances of that program on the same machine, I'd be in trouble because they're all going to listen on 8080. But in a Docker container, we can change the port mapping. So what we're telling Docker here to do, we're telling Docker run -d because we want it to be a daemon. But let's do port maps with it. So we want it to be 9090 on the outside of the container and 8080 on the inside of the container. So we're going to tunnel it through. So this is part of the feature of the Docker daemon is it's creating effectively a little NAT environment that all the Docker containers live in this NAT, and they are going to be routed through all of their ports are going to be mapped in and out. So they're also kind of firewalled as well. So not only can you play with their network ports, you can also kind of control which ports they have access to in and out. So I think this is going to be the run shell script. Let me make sure. Oops. Yes, okay. So we'll run it. We have a container. I think I did open. Okay, so there's our program. It's not very fancy. Every time we refresh it, it's updating the number. That's pretty spiffy, huh? Now we can go in, back over, and do some things like, so we can stop the container. So remember, we're writing the counter in a text file on the file system of the application, which is in the container. So it's writing it on that writable layer of the file system in the container. So if we stop the container, let me make sure what stop does. Yes, so we just killed it. We can do Docker PS. We can see that it's not running. PS-A, it's still there. It's exited. We can start it again. Did I have a start? Yeah. Yep, okay. I have to double check in on my shell script so I don't screw stuff up. So I've restarted it. And we can see it there, PS. Now it's running again, same one. So it's the same container that we had killed. It was stopped, and we started it again. All the process state with the CPU and the processes were lost, but then it's restarted. It can kind of come back, but the file system was retained. So if we go back to the website and we refresh, it keeps counting. So one thing I didn't show you, which I should have showed you here, is if we stop it, it stopped again. Now we try to refresh it. Oh, it's not there. We can't talk to it, of course. Okay. Still counting, continues to count. That's because the state is saved there. I think, let me see if I remember the Docker command. Copy. Yeah, I think we could do that. Oh, I might have done it already. Diff, okay, yeah. So I wrote a little shell script here that will copy a file from inside the container. So Docker CP command will let you copy a file from in the container out to a local file. So I'm going to copy the data counter file from the container out to my Mac, and then we're just going to cat it and then get rid of it. So this is just a poor man's way of catting from in the container. So I'm going to cat it, and we can see, 14. So that's what the contents of the text file inside the container, and that's the last thing we printed. So that's all pretty good. But now let's see what happens if we kill that container. I'll remove the container. Let's see. Okay, it's running, so we want to kill it first, so we'll stop it. Stop it, like we did before. So we were able to stop and start it, and the state of the counter was in the file system. It's still there. It was fine. But now we'll remove it. And then if we run it again, let me go back and refresh. Start it over. Because at that point, when we removed the container, that writable file system that kept our state was removed as well. So if you're going to use Docker to hold the database, you probably don't want to write all the data for the database into the container and then forget about it, because it will just go away. So that was the demo. Any questions on that? So the main things we wanted to illustrate with that demo were the network ports, so the port mapping, and sort of the transient nature of the file system. That we're just, basically the way to think about that writable layer in the container, it's really good for making another image if you're writing and saving it as an image. And it's also very good for scratch files, temp files, things you need to write, or things that you've read from the network and you want to write to the local file system as cache. That's a great use of that writable layer. But for permanent storage, for something serious, you don't want to rely on that. And it's also not going to be as performant because of the virtual file system. Writing to the top layer is less performant than writing to the actual local disk. So the next thing is we're going to go one step farther. So we added networking to containers. Now we're going to add volumes to containers. And I may have jumped ahead of myself. No, I didn't. Okay, it's good. I'm going to make sure I know which demo is the right one. It still is, okay. I'll make sure I'm running the right ones now. Okay, yeah. So now we're going to run the same program again. Same container, same image. Well, same image. Run the container, but I'm going to run it a different way. So we're going to learn how to type. We're going to run it with one more command line. So in addition to the normal Docker daemon, run it in background mode, map the ports, we're going to mount a volume. So I want to have something that's more persistent than my container that I can manage from my host. So in this case, I'm using the -v command to tell Docker to mount a volume. So we have to tell it what volume we want from the host and where do we want that volume to appear inside the container. So the first part is /home/Docker. So I'm just going to map the home directory inside that tiny Linux. I'm going to map it to /data inside the container. So we'll do a vrun. Ooh, oh. Cleaning up the old one. Well, first kill the old one. Kill the old one, clean up the old one, run the new one. Okay, so now the new one's running. We can go here. We can see it starting from 1. It's counting. Okay, that's really good. Go here. So one thing we can do, you saw that we've mapped /home/docker to the data volume. So the container's writing into /data/counter. It's happy. It's where it's saving its state. We can do, remember, boot to Docker, SSH. Now we're inside the Docker container. Sorry, I don't want to confuse you. It's the wrong word. We're inside of the VM with Docker. So we're inside of the VirtualBox VM. We're in /home/docker. We can look around. Oh, look, there's a file called counter. Cat counter. It's at 8. It's a little hard to see, but it's at 8. Bottom left there. And that's where we left it. 8. So if we count this guy up again a little more, go back inside, look at counter. So we've seen now that we've just effectively done this directory mapping from the host directory to the Docker container file system itself. So it's mapped sort of virtual file system, but then mapped over to an actual volume that's attached. Now, we've just picked some random local directory that was convenient to map. What you probably do in the real world is actually attach some kind of remote drive or have a physical disk. That's a particular mount / some external hard drive. Then map that whole drive to the data volume for maybe a database running in a container. So that way you would have the real database app could be the application bits and the configuration could be deployed in a Docker container, and then you manage the actual physical storage, or maybe it's a SAN mount or something that's a more reliable, self-contained block of storage that you would then attach to the data volume this way. So any questions on that? Okay. Let me make sure I didn't have any other useful things to show. Okay, I'll show you one more thing, is that I'm going to shut it off and then start it again. That's kind of what we wanted to prove, right? Stop. RM. So it's gone. No more container. Oops. No more Docker containers. He's not running. You go back in and do vrun. Start him back up. Refresh. Oh, still at 22. So that was his persistent store. Is lived longer than the container. So that's what we wanted to show there. So with the mounting, there was the demo. We saw it. Okay. So now I think a few people came up to talk to me, but in the break, and asked me about sort of best practices around how much stuff to put in one container. And basically my advice was to if you're stacking different libraries together to build up your app, those belong in one container. So you have your Linux base, maybe you've got your JVM, and maybe you've got, what else might be part of the library? Tomcat. Those are all things that are part of the process of the application you're building. Those belong in one container. So at runtime, at process time, that's one thing. Now you're going to want to make use of layers for your images so that you can reuse those layers and keep them nice and lean and stack them up. But that's one process. Then if you were running Apache, you probably want to run Apache in another process, so that could be another container, and then you've got maybe Postgres, MySQL, maybe you got Memcache. Those would all be nice process-oriented things to have in their separate containers. Each one would have the libraries that made sense for them, that was part of their runtime. But when they're running, you have nice process separation with the containers. And they talk to each other through their networks bindings. Now, you could do the commands I showed before with just the -p for setting the ports, and you could connect them all up yourself. But Docker provides a command line tool. One of the options is called link, that you can sort of let Docker dynamically allocate ports and then connect them together. But I'm even too lazy for that, so I'm going to show you how to use another tool called Fig, which is really handy for launching a bunch of containers at the same time. It's a really simple little command line tool that kind of works like you use a Docker file to create one image for you. Fig can be used to launch a handful of containers in a very repeatable way. So we want to build something like this, although we're not going to do Rails and Postgres, but we're going to have a couple little programs. We want like a declarative way to just launch one container, another container, allocate some ports, and then connect them together. This was just the closest picture I could find to steal. So what we have is a couple little programs. So now we're starting over, new language. These are things I just found as good examples to show. So I'm not a Python guy so much. But there's a nice little program that is a Python program. It's a little web app that's very similar to what we've already been playing around with just a hello world with a counter. Uses Flask for its web environment. Uses Redis to save the state of the counter. So the library stuff that's related to Flask and Python and all of that, that's part of the image, and that's the container, that's the web app, which is the Python web app. The other container will be Redis. And our Python Docker file looks like this, very simple. We started with an existing Python base image. So from Orchard up, it's probably sitting on top of Debian, which is going to be bigger. We could build it ourselves if we really cared about efficiency. We could build up a new Python base for our teams that are doing Python and start with BusyBox if we wanted to do that. But this is really great because it's already done and tested. There's a number of like sort of language development environment containers that are available on the Docker Hub that are kind of handy to definitely to just go play with. And if you really like them and you want to use them, you could look at how they're made and maybe make your own forks of them to make them more efficient. But this is how we make our container. In this case, we're using, so this is a new case. In all my other examples, I used the add command, which tells Docker during the build to add a file from my external environment into the container. In this case, we're doing a run command, which happens at build time. Even it sounds a little confusing, but it runs it in the container at build time to install something or copy something or move files around or do something. In this case, we're just doing a pip install to get the program into the container. And also primarily to get all of the requirements. So that's how we're getting Flask and the Redis libraries into the container. And so Fig, here's some doc on Fig. The other way to do it is just to write lots of command line calls to Docker yourself. So Docker this, Docker this. So you could sequence a couple of Docker command line to do the equivalent thing. But I just wanted to show an alternate way to do it. That's pretty handy. So what we end up with is a Fig. So this demo is called Figgy. This is the fig.yaml file that describes what we're going to build. It says how to build the containers. It says what ports we want. We want to port 5,000. It talks about which volumes we're going to be managing and mounting. So everything we've seen before that we were doing with Docker directly with the Docker command line, this is just sort of automating for us in a very nice declarative way. And then we say, oh, it links to Redis. So it knows it needs to talk to the logical thing called Redis, which is the guy in the bottom. And that's a simple container. We're just going to go get an image that's Orchard Up's Redis and just run it. That's it. So this is the whole declaration of our two containers we want to run together. So that's our app. That's it. Yeah, so I don't even have shell script in here because it's so easy. Fig up. So it's done. And then where did we put it? Okay. So it's on port 5000. Let's see, you have to remember that. Yeah. So it's the same port. So this URL that I've been playing around with here is the URL that boot to Docker has exposed my inner Docker runtime as on my Mac. So we'd go look at port 5000. That's now talking to that Python app inside the container. And I can refresh, we're counting. It's very impressive. And I can kill it. You can see the log. It's been logging all the gets that we just made to it. And when I kill it, the fig environment takes care of shutting off the containers correctly, and they're all nice and shut down. And we can see that we can't reference it anymore. It's dead. We'll bring it back up. Still counting. So Redis was able to save off its state, if that's what it is. It's a database. So it's got a volume out where it's saving everything. So that was much easier than our hand managing of volumes. But this whole same thing with Fig can be done to put together environments that are much more complicated. And you don't care about exactly, well, what port did the Python Flask app use to talk to Redis? Well, Fig figured it out and let Docker figure it out and just connected them together. We don't really care. It just worked. So that was fine. So any questions on that?
So they are both running in two different containers?
Yes.
And are only the needed ports open between those containers?
Yes.
Or just everything is allowed in terms of communication in both directions?
No, so only the ports that were actually needed between the two were opened. I'm not sure exactly in the case of Fig how it knew which ones to open. Oh, so one of the things that you could do, it's probably this case. I didn't research this one for this example, but when you create a container, there's a couple things that you can specify as metadata. Like we saw the command to use to run the container. What executable to start inside the container for your command or your entry point. The other one is what ports you want open. It's like with our little hello world, we said 8080 because we knew it because we wrote the code, right? But we could have put that in the container and we could have said expose 8080. So it becomes metadata that says, hey, I'm going to listen on 8080, and if you want anybody to talk to me, hook them up to that. So that's probably what Redis did. And so when Fig said, oh, he wants to talk to, the Flask app wants to talk to Redis, Redis is listening on port X, then I will make sure there's a link between those two and tell them. And then it can also pass in the environment variables to both containers to let them know where the other one is if they need to know. Yeah. Okay. There's a couple other little handy things you can play around with. So there's a little tool called C Advisor from the Google guys. So I think it was from the team that had a project. I think it's called Let Me Contain This For You, which they were working on a year ago, that time frame. It was a way to manage containers, and some of the tools they came up with are very useful. So they've sort of morphed that into a newer project, which we can talk about later. So once Docker came out, Google jumped on that too. I mean, everybody recognized that was kind of a really great, common, standardized way of dealing with things. So all of the other low-level tools that were dealing with Linux containers just sort of dropped what they were doing and moved over to Docker. But this tool is still useful in the Docker environment. It's C Advisor. It's a container advisor. It lets us look at what's going on inside of a container. So it's a GitHub project, and go grab it and play around with it. It's also on the Docker Hub, so that's where I'm getting it all from. So let's kill that guy. Ooh. Let's see. Remember. Start, stop. I remember how the demo works. I bet we start it first. Yes. So we're going to do Docker run and mount some volumes. So this container, this program's in a container. So that's nice. It's easy to deliver it. But its job is to actually do some really low-level things with the Docker world. And if it was just in a container by itself without any access to the outside world, it's just going to see its own little file system. It can actually see outside of the file system that we've given it. So it wouldn't be able to do much. It wouldn't be very useful as a system utility if it could only see its own self. So what we've done here in its run is we've managed to map its internal file system onto the host file system in places where we want to have it look at things that are going on the host. So you would definitely wouldn't want to do this with like foreign random applications and let them map stuff onto your root file system. But if you want a utility that needs to get to stuff that's low level, you can still do that if it's in a container. You just want to. There's different ways of doing it, but this is a really nice way to do it. The Docker's runtime, like all the information about the containers that are running, are in /varlib docker. So mounting that into this container lets this container snoop around and see what's going on. So we'll run it. Oops, start it. There we go. Okay, so it's running. Oops. There's the container. Oh, we left the old one up. Okay, well, I'll leave it up. Open. So there's C Advisor. So this guy's running in a container, but he's also showing us what else is going on. He's given us some information about what the OS sees, so what kind of CPUs. We have 1,024 CPU shares, so like fractions of a CPU. We've got 8 cores available that Docker's allowed to allocate stuff to. This container doesn't have any memory limitations or swap file limitations, and there's sort of an overview of the consumption of CPU and memory. And you can sit and watch the CPU usage. So this is a really nice, so Google's got a new project called Kubernetes, which I'll show you a little bit about it going forward. And this is a typical, basically like a monitoring daemon that sits on the host and watches all the containers. And you can query it with a REST API, look at the web dashboard and see what's going on, what's happening with the cores. And you can drill around also and look at what's going on with the container system, file system here, what containers are running. Docker. C Advisor is one container, and the web hello go is one container. So you can basically browse with the browser or with REST calls and so probe around and find out what's actually happening on the machine and what kind of resources this particular container is using. So this would be a way to find out if some containers are using too much resources or just to monitor things, keep track of what's going on. So it's a very handy way to get some insight into your container environment. Let's see if there were any other interesting. Oh yeah, okay. You can also hit, it has a REST API, as I said, so you can find out a lot of the same information that's on the web page. It's available through the C Advisor's REST API. So things about the machine capacity. How many containers are running on it. You get a basic summary of information about all the containers. Now there's a few things that I've dug up and you can hook it up. So C Advisor can be connected to InfluxDB and you can run Grafana on top of that. So you can have some really nice graphs that are monitoring the CPU usage, any kind of resource usage of your applications. I didn't get that finished up, but there's a starting bit here that you could play around with if you pull down the GitHub. There's documentation for C Advisor on how to set up its communication with Influx. Okay. Yeah, extra credit, hook up Influx and Grafana. Grafana's got some really nice web UI. I wanted to get that going, but just ran out of time. And there's another thing you can do. So if you imagine all your hosts are out there running, they're running Docker, they've got maybe C Advisor on them all. There's another tool called Heapster, which is currently, I think, really targeted towards the Google Cloud platform only, but something like it, or you could grab that and maybe hack it for your environment. But the idea there is to aggregate all of the C Advisors across your whole space of hosts into a common UI and then show a whole aggregate of all of. So forget about what host your containers are on, just show me all about my containers in one big large sort of pool of graphs and charts. So that's another interesting way to go. So I probably will be looking at some of those things for my project too. So the next thing I wanted to talk about was Docker is really great for development. There's lots of things you can do just to use it for sort of isolating things on specific machines, and even managing machines the way you're managing them individually, putting Docker on it, running things on node machines, very specifically using like Fig or shell scripts to launch and stop things. You can still get a lot of benefit from that. But the real big win becomes when you start to think about Docker containers running on giant fleets of machines. Or clusters. So typically we'll call that a cluster, right? So you've got maybe dozens or hundreds of machines all running Docker daemons, all running the same OS, and all just being there to run Docker. So it'd be like, imagine you've got Docker containers running on one cargo ship. That's like one machine. Or you can have an entire armada of ships carrying Docker containers. And you can load up the containers on whichever ship at any time and move stuff around. It can be very dynamic. So you've got this sort of cloud-like environment without having the virtualization to worry about with clouds, and the efficiency of all the tiny Docker images that you can move around. So again, the benefits are, so the Docker containers are black boxes. And somebody had asked before, and I was going to bring this up and come back to it. You typically will want to build your Docker containers once. So you've built your app once, you've tested it, you've built it in dev, you built it with CI. Once you've got that immutable artifact in your registry, you'll test that in the different environments and eventually move it to production. You want the bits to be the same because you want to know you're running what you tested before. But you do need to provide different context for the app when it's running in a different environment. So there's a couple of approaches to that. I think I have the picture. I did a good picture for that. But that's one of the main things we need to solve. So we need to solve how to get different configuration to the apps, because that's sort of supplemental information in addition to the binary of the program that we want to run. And then kind of a separate class of configuration, I like to pull it out and think of it separately, is the service addressing. So if I have this big SOA graph of services I want to run, and I know I need to tell this middle tier layer where all of the machines are that are running the tier below it that they need to talk to, I need to supply that information. And the reason I like to think of those two separately, or just pull this one out of the config problem, because often with like Chef, people will just do that kind of as dynamic config. It's just the config that's done when you install. If you're doing things in a cloud-like environment with Docker containers, your downstream services that you need to talk to may be moving all the time. So you really don't want to do that with a static config, that's sort of an environmental context configuration. What you really want to do is do that with a different mechanism. So let's solve those separately. So here's kind of the picture of it. When we deploy the little blue Docker container, at that deployment time, we'll do the Docker run equivalent. And we can pass in additional command line flags to the program when we're starting it as part of the Docker run command. We can also pass in environment variables. So command line flags are useful in some cases, but the sort of idiomatic way to do it with Docker is with environment variables. It's really very useful. So if we're deploying to prod or deploying to test or deploying to like staging environment, you might pass in different variables that will tell your app how to deal with or what environment it's in. So like in a project I'm on now, we have some specific variables that we just call like they're basically location, data center, shard, and environment. And those variables are what tell the app how to look up and find its dynamic configuration. It tells it where it is. Then in our world, what we do for the second phase, how do you find your other services you want to talk to, is we use the same pattern that Netflix uses with Eureka Discovery. So one of the things that once we get the configuration passed into the application, and these are primarily, Java apps and Go apps now, is it'll use its location information. So it knows what environment it's in, it knows what data center it's in. It'll use those two bits of information to create a DNS lookup, go get the DNS lookup and find, that will tell it where Eureka is. So then it can find its discovery service. It'll then ask that guy where everybody else is. So that's just bootstrap. You just need like one little bit of information to tell it where the rest of the world is, and it will just bootstrap itself up and find the rest. And the advantage with a system like Eureka or any other sort of dynamic discovery system there is if nodes come and go, or a downstream service cluster is loaded, overloaded, it can expand, you can add new nodes to it, and we'll just pick those up in our new address resolution when we need to talk to them. Nobody else has to be updated, just the shared discovery service. Another approach to doing that some of the clustering systems do, like Kubernetes, I think that's the main one right now, and other things that are built on top of Fleet, will do it by managing ports and natting and doing some network magic for you. So in the case of doing it the Netflix way, you have to have knowledge of this Netflix way. This shared discovery service has to be part of your app. Or you have to create some kind of adapter yourself and deploy it with your container, which is not too hard. And if you're building your own, if you're starting from scratch, or you're basically doing a nice update evolution to SOA with your application environment, then this is a good way to do it. It's a nice and clean, and it's well proven by Netflix at scale. But if you have a lot of other apps that are legacy apps, or you just don't want to rewrite everything, doing it with sort of a network adapter layer like Kubernetes does, it could be another alternative too. So I'll show you some cluster things. I hope this works. Oh, I need my phone. So I created a small cluster in AWS, but it's running in California, and it's in the VPC. So I have to get on the VPN to get to the VPC in California. Looks green, that's good. Okay. So the cluster looks like this. So I used CoreOS. I just launched 5 machines in an auto-scaling group in the VPC, grabbing standard CoreOS distro. I just found the one they said was a good one and launched it. I think I included it here. They're configured this way. I didn't set up etcd, so etcd is not really running. And the machines don't know about each other at all. They're just sitting there. But what I did is I tweaked their Docker command line so that the Docker on those machines is now listening to a TCP port, just like our local boot to Docker dev environment is. I mean, this is not, and there's no TLS, there's no security. It's just Docker's listening wide open on a port. I don't want this on the open internet, so that's why I did it on the VPC. Because you can basically tell those machines to do anything. And then what we'll do is locally, I'll have a little shell script that will run Docker on all the machines at the same time. So it's kind of like a poor man's cluster. So I grabbed, these are basically samples from the CoreOS website to tell it how to do its cloud init to start up stuff. So this is the trick if you want to tell it to start Docker at startup time, but also listen on external port 2375. So it creates a little socket unit that will then listen and pass it over to Docker.
What is CoreOS?
Oh, sorry, what is CoreOS? So CoreOS is very interesting. It's a Linux distribution that's pretty new. The guys are in San Francisco. A lot of them used to work at Google and worked on Chrome OS. But their goal is to make it's a very small Linux distribution that is based around Unix containers and systemd. So it doesn't have any of the other boot runtimes. It's only systemd. Everything is done with systemd units. And when it starts a very minimal stuff. And if you want it to do, you can configure it to start different things at startup time. And you do it with its cloud init, or there's different ways of passing the kernel, the boot init information to it. And on AWS, it's super easy. You just pass this into the launch config when you launch it. But the idea is that the OS can self-update itself. All applications run on it are in containers. They don't have to be Docker, but they have to be containers. Docker is really easy to do. Everything installed on it's in a Docker container. The OS is separate from the apps. And so it lets you sort of refresh and rebuild and update the OS underneath the Docker layer. So it is basically built from the ground up around this separation. So and it's very small and handy to use. It's great for deployment on AWS. Probably other clouds as well. I haven't used it. Yeah, so there's the rest of the cloud init is basically wiring up Docker. And now the demo. Okay. Clusters. Okay, I have one shell script called doll. So it's Docker on all. So it's very brute force. I'm not a great shell programmer. But the idea here is, like when I run this, I will run something on all 5 machines. So it's going to run just a Docker command. We already know a bunch of Docker commands. So I could say doll ping. Well, let's do something version. So it just sequenced through all 5 machines, did a Docker version. Okay, we got Docker, they're running, my network's working, that's really good. I was worried this whole thing would fall apart when I got over here. So the Scout program I showed you before can be run. I always mention it during the images. So Scout's just a little program that will run. It's a little web service, RESTful kind of API that we use internally. It's sitting on the registry back at work in Los Angeles. And I can tell all 5 of those machines in the data. This is in US West 1 in Fremont, California. I can tell each of those to run those 5 programs. And it's sort of a little mini cluster thing. They should just all do it. So I could say run Scout. Oops, oh, there's already one running. Oh no, I forgot to clean up. Okay, well we have to troubleshoot. So we'll run doll and let's do a PS on all of them. Okay, there's none running on any of them, but we can do PS-A. Oh, look, I left them dead. Okay, so now I can do is an RM Scout on all of them, cleaning them up. And then we could try to run it again. So starting containers. They're going. And now I can do PS. Oh. So this is what happens when I run stuff that's being pushed sort of dynamically to our registry. So this guy's broken. We can debug it really quickly. Yeah, pick one of these at random. They all died the same way. Let's run Docker on one of them and tail. Let's say logs Scout. Aha. Yeah, so the program I ran, which was probably built since I last tested it, is trying to connect to the Discovery service. It has some basic configuration, and we did it wrong. And so that, as I mentioned before to somebody who's asking me about environment, so we're passing in here RC environment is dev, RC data center is Las Vegas. But that's really not where it is. So yeah, it's not finding its config file correctly, so it just aborts. So this is what happens when process in a container just exits, that the container's done and it exits, so it stopped. So we were able to control the machines, and I was able to tell it to do that. We could try to run something else. Now in theory, I could run the little programs we wrote today, but I haven't pushed them anywhere in the registry, so I can't get them to Fremont very easily, unless I put them on the Docker Hub, but I hadn't done that yet. But we could run, let's see. Yeah, we could run something. we can run Ubuntu. Debian. Well, I'm not sure. That might take a little while. Does anybody want to see more of this one, or are you ready to move on to something else? Okay, I'll move on. Okay. So for the rest, now I have to apologize. I had a demo for this one, but it broke as well. So I'll walk through how it works. So part of the distribution of CoreOS, so some of the technology that the CoreOS guys have done, in addition to their sort of nice self-updating, immutable version of Linux, is they have a daemon and a distributed configuration tool called etcd. So the idea with it is it's a clustered, distributed, Etsy as being like the Etsy directory full containing all of your config. So it's sort of a what do I say, cluster. Here's a good picture of it. A way of clustering configuration across a bunch of machines. So you can effectively have almost like Zookeeper, but running with lots of little daemons on each host that find each other and share information, and then replicate the information that you need to move and replicate between them in a way that's very easy to use. So from the consumer side of etcd, you hit an endpoint at a fixed port, like 4001, and what you get is a REST API to a very simple file system that you can use things like, you can have counters and locks and just simple config values in there, sort of like a little Zookeeper. But in the backend storage of all of that will be replicated between the machines. Then on top of that, because on every CoreOS machine you're going to have etcd and you're going to have Docker, you could use that distributed etcd to also control your Docker runtime. So they then have a clustering system called Fleet. I don't know, yeah. So this is so similar to the Cloud Init that I used to start up just the Docker in the sort of debug mode, putting its port out. There is a way that you can start CoreOS to run Fleet in the Cloud Init. And this is all on the CoreOS website. It's easy to play around with. It works pretty well until every once in a while, well, in my case, they stopped talking to each other, so that wasn't very good. But there's a way to bootstrap them so your cluster can find each other and then they can come up and keep running. So you have to have at least 3 nodes to keep the etcd quorum working, but then you can expand it to as large as you want. And this is how you talk to Fleet. So there's a command line tool, like Docker has a command line tool to run, you just run Docker to talk to the Docker daemon. With Fleet, you run Fleet control to talk to the Fleet daemon, and you just give it one of the endpoints. So you just pick any one of the machines in your cluster, and you tell Fleet control where it is. And the port, it's actually going to talk to the etcd on that machine. And then it will do our clustering things, like our homegrown cluster, so that we can launch containers. Fleet will do it by talking and putting container launch information into etcd. And then it will cause the containers to be started in different places. And this is what a typical declaration of what you want to do. You create a service file, which tells Fleet what you want to run. And it's really kind of it ends up being a systemd startup. So it's really what Fleet is doing is helping you distribute systemd service definitions to all of the machines and telling them to run it with systemd. So that's pretty solid. In this case, we're running a little test that is, how do you start it? How do you stop it? You have to tell it all these things. We're just running BusyBox. And these are the commands that it's doing. Systemd doesn't implicitly know about Docker, but it can run Docker commands just very simply like that. So our actual run command here is just the hello world sleep shell script. So that's what would be distributed by this guy. In the demo, I can show you the commands, but it's not working right now. Also, same kind of thing, but if you made your own, I had some hosts here that were running in the same VPC that were set up with Fleet. Fleet control is here, so if you pull this down, run it on your Mac pull it down from GitHub, run it on your Mac, you'll have Fleet control, and you can run these. and the services are here. And then, for instance, the submit, this is how you submit services to Fleet to tell them to be run. So they're ready to run, then you can tell them to run. And they'll be run on all the different machines. Okay. So no actual demo on that one, sorry about that. And a couple more I'll talk about, but I don't have any demos prepared for these, but I can give you kind of an update on where so what's the state of the union for this sort of clustering technology. So Mesos is an Apache project. It's been around for a while. It started out as a grad student project that grew really big. Twitter uses it. It was built around containerization. It was modeled after the Google Borg runtime environment. I think the guys that did the project did it based on some white papers from Google. So they said, well, that's a really excellent idea. Let's build that. And after Google had committed the kernel extensions for C groups and namespaces to the Linux project, well, then everybody can now leverage it. So Mesos takes advantage of that. It has a very strong architecture. I think I have some pictures, yeah. So there's this basic layout. You have one master for your cluster with a couple of standbys. The leader election is handled by Zookeeper for that. But pretty much, if you're just playing with it, you can run one master, and that's fine. And then every worker node has got a slave process on it. And the master figures out how to schedule the container that you want to run, figures out which slaves it should run it on, tells them to do it, they do it. The Mesos guys have integrated, they started integrating Docker last fall, and the first couple of generations of that were really a pain to use, and they didn't work very well. But as of, I think, a month ago or 2 months ago, the Docker integration is much more tightly integrated into Mesos, so it's more first class. So the idea of containerization and delegating to Docker to do the work is much cleaner than it used to be. So that's something. I haven't looked at it recently, but I will definitely go back and take a look. It's worth looking at if you want to play around with something a little bigger than little test programs on a tiny cluster. And the architecture between the master and the slave, that is really rock solid, production ready. People have been using that for a long time. It's just sort of the Docker integration that's new. So definitely that is very efficient, very fast. They use Google protocol buffers. The core stuff is in C++ for the master-slave daemons. They're fast and small, don't use a lot of resources. Do any questions on Mesos? No? Okay. Another one is Kubernetes, and that's sort of the next generation of the Let Me Contain That For You project. There's a bunch of work going on here. It's open source. It's a really nice project to follow. These guys really are like doing a lot of the latest work in this area. They know what they're doing. It's really interesting stuff. So it's completely based around Docker. So it's not something where Docker was added on later, like Mesos was. It's available on GCE. So some of the things that the Google Cloud guys, so the cloud team, is incorporating this functionality as well. So you can effectively get Kubernetes as part of the Google Cloud platform, sort of built in. So that's pretty exciting. Their architecture, I don't know if you could read that very well. So the guys on the right, those boxes, they call them minions. That's their slave or their host machines. It's running Docker. They use a little daemon they call the kubelet that is sort of a proxy for talking to Docker, that they use between the master and the Docker on each slave, which is a good idea, not to have your master have to reach in and talk to all of the Dockers on all the slaves. You go and have somebody in there helping you out. So that's what the kubelet does. C advisor is the same C advisor we saw before. That's what the kubelet uses to monitor all of the containers that are running on there. And then they bundle their containers into little packages that they call pods. So like our example where we've used Fig to launch up a couple of containers and tie them together, that same model Google does supports and calls it a pod. So you wouldn't use it to distribute lots of tiers of your application in a pod, but you might use it to have a logical service that took more than one container. And you want to call that one thing and deploy it as one deployable group. So it's a tightly coupled set of 1 or 2 or 3 containers maybe. So that's what a slave looks like, those guys on the right. And on the left, what you have for dealing with distribution. There's a scheduler. There is replication controllers for keeping track of how many of certain containers there are, where they should go. It exposes a REST endpoint so that you can talk to it from a command line tool or from another service that's driving it. And one thing that Kubernetes does that's different than some of the other ones is it does have this notion of this networking layer. So it manages the containers and how they see each other in a different way, and it has its own opinion about how to do that. And if that works, it's really handy because it will do it all for you. But they basically associate a service, a logical service, with a port. And so your ports are constant. So if you want to talk to a service, you go and you know its global port address, and you just use that. And then that will be mapped across the actual real network over other ports, and then eventually routed to the various services on different machines that will then be adapted to that fixed port. So it's a very interesting way to do it, but it does require more than one IP address per host because you have to be able to have a fixed port with variable addresses. So it's an interesting approach. The reason I haven't even looked at it for my project at this point is because we already figured out how to do our network routing by doing discovery, service discovery. So we don't need that part of it. But we still might grab some of the other bits. And in fact, the project I'm working on, we modeled our declarative container, our deployment description kind of language on the pod language that Kubernetes uses. Okay, and I think the very last thing I wanted to talk about, did I do it? Yeah, very simple description of what my team is building at Riot. We're basically rebuilding the next generation deployment system. We've looked at a lot of these other technologies, and for the time being, we're building our own because a lot of these other ones aren't quite ready yet. They're either, like Mesos is really solid but doesn't do Docker that well. Some of the other ones like Fleet on top of CoreOS is kind of tied to CoreOS, and it's kind of, the etcd implementation was not high performance and scalable at the time. It's getting better all the time. But 6 months ago, it was a little bit limited in larger clusters. So we wanted to do is start our own. And at some point, if we decide something like Mesos is a better transport, we'll rip our back end out and replace it with Mesos. But our model really looks like the first picture I showed you. We're running OSs that are just exposing Docker. We don't care what the actual OS is. If it exposes Docker like I showed with the first poor man's cluster, we can talk to it. So our system is called Admiral, just a cluster manager, presents a REST API. You hand it a definition of a pack, we call them packs, and then it will follow some kind of rules. You give it some, I need 5 packs running on, make sure they're not on the same machine. We can handle things like that. And we'll say, okay, fine, let's put 1 on each machine, spread them out, launch them. It'll take care of talking to the Dockers on each of those machines and start the containers. So it's really just sort of the next level of a service that can enforce a desired state across a bunch of different Docker hosts. If a container dies, it can restart it. If a host goes down, it can start the containers up on alternate hosts. So that's kind of what we're doing. And that's the end. Does anybody have questions? Yeah. Oh. Thank you. Yeah.
Quick question about the placement of the Eureka service.
Right.
In this presentation, you had the arcade thing where you have a master, where you have all the place that set up like that. And I'm just putting it on the machine with the F.
Right. So the question was regarding how the placement of the configuration. Yeah. So, well, in the case, what we're doing now with our current environment at Riot is our Eurekas, or our own, we have an implementation of Eureka that's an alternative, but they both work the same way. We use DNS text records to keep track of all of the nodes in the Eureka cluster. So they register themselves in a text record with URLs. And so all you need to know is then, well, what's the address to look up the text record, which is always formed by building this fixed string that contains the environment in the data center. So the only strings we need to tell the the service is what environment, what data center are you in? Or you could give it a full DNS name to go look up that text record, but you don't need very much. It's similar, I think, so that's sort of the bootstrap. I forget, it's not Archias, but it's the other Netflix library that's used for the Eureka client. So you look up Eureka first, find out everybody, and then Archias looks up the configuration data after Eureka. I don't know. If you could ask me in person if you want to talk about it afterwards. Are there any other questions?
Maybe a simple question.
Yeah.
If you stop and start the engine, maybe if you want to replace the engine, will it restart all the containers from the same state?
Yeah, the question is if you start and stop the Docker daemon, right, will it restart the containers? It used to have problems. I think it's pretty reliable now that it just comes back up and picks up where it left off. The state of the running containers is in the var lib Docker. Some of that's kept there. The rest of it's in the kernel because they're running and it can find them again. And like all the metadata about the process groups that are that are running the containers is sort of saved on that graph part of the file system. And then if you restart the daemon, it will figure out and pick up where it left off. Yeah. Okay, it looks like it. Thank you, everybody.